Hey everybody, this is Larry. This is me doing week 2 of the October weekly challenge or whatever. Hit the like button, subscribe, and join me in Discord. Let me know what you think about today's problem. Today we have 774 minimize max distance to gas station. A hard problem. Okay. You are given an integer array stations that represent the position of the gas stations on the x-axis. You're also given an integer k. You should add k new gas stations. You can add them anywhere you want, not even in an integer maybe. Let penalty be the maximum distance between adjacent gas stations after adding k new stations. Return the smallest possible by your penalty. Answers within 10. Okay. I mean, I think this seems pretty. Actually, am I right? No. Actually, I'm not gonna lie. My first impression when I was like, "Oh, this is simple, right?" It's just a heap problem, where you just look at the distance and then you greedily loop k times. K is a million, so maybe not even, but you just choose k times, right? And you loop k times. You do a heap, and you just divide the portion in half. But that's not true, is it, right? Because if you could, I mean, there are at least 10 stations, which is a thing, but you can imagine you have a thing where, you have 1 and a 5, and then maybe just a lot of numbers. But instead of dividing it from 1 to 2.5, and then, because actually the middle is 3. But instead of doing it from 3, you could also imagine maybe you do, divide them in thirds, right? So then now, okay, maybe that's not good. Not good. Let's say 10. Instead of 5.5, you divide them into 4 and 7 or something, right? And maybe that's more optimal. You have two. If you have k is equal to 2, and those are your two choices, right? So definitely that's not quite right. I think the actual idea is going to. My other guess, honestly, my second guess, but after realizing that, the test case that I just showed you, so that it wouldn't work as a greedy heap type thing. The second, I'm not gonna lie, is that what was my second idea? Well, I saw that n is equal to 2000, so I was like, maybe there's some dynamic programming type thing there. Wasn't quite sure how to do it, especially since k is equal to 10 to the 6, right? As we're talking about it. But the strictly increasing order doesn't actually matter that much because, because you could just sort it, so it's not a thing. But then it occurred to me, of course, that you could just binary search, and in this case, I think people call it binary search for the answer, which I don't, I'm not a fan of necessarily. But I think and that would work, right? Because then now you're guaranteeing the penalty is the number that you're binary searching, which is going to be, yeah, right? And then as a result, then yeah, I mean, I think that's it. I mean, it shouldn't be that bad, right? Yeah. Because the idea here is that then now the binary search allows you to be greedy, right? So for example, if you're searching for, if you binary search for the answer, for example, if the answer is, or your target, I always call it target in a binary search, like what you're targeting. If the current target is say 5 and your current place is at 23, then you just add one at 28. That guarantees that the penalty is at most 5, right? So you kind of think of it that way, and then when you run out of k, then that's no bueno. If you have enough k, then you try a bigger distance, right? Or a smaller distance? Yeah, no, smaller distance if you have enough k. So yeah, so that's it. That's going to be the idea. Not too bad. I mean, I think, yeah. So here we set up a binary search, right? Keep in mind that each station can be 10 to the 8, so that means that the biggest penalty is going to be 10 to the 8, so we could do that, right? Right. Is 1e8? I actually don't. I always confuse where 1e8 is. Or 1e9 maybe. I don't know. No, let's just write 10 to the 8, right? More specific. But these are binary numbers or binary. What is it called? Man, I don't English well. These are fractions. No, they're not fractions. They're what is it called? Decimal numbers. Man, if you're watching this in the future and didn't watch my daily video, I just ran 11 miles. It is 3:40 a.m. I am pooped. and I have, so that's my excuse. But in any case, yeah. So you could write something like this. You can maybe even add a tolerance, right? Some epsilon, right? But actually, what I usually do, honestly, is I don't even worry about it. I just do a for loop. And a for loop you could do, I don't know, and it's just a function of the math, right? You can maybe do it 100 times, right? The reason why, and maybe 100 is even too much, honestly, but remember that for every binary search, you get one more bit of position. So 100 bits or 100 iterations will give you 100 bits of position, which means that that is going to be way small. It's going to be like 2 to the 100, right? In terms of position, which is going to be way good enough. The only question is whether this is too slow because you have 100 loop times, you know, something that goes over every station. So 100 times 2,000, it's 200,000, which is fine, right? So yeah. So then now we go mid is you go to left, you know, just regular binary search stuff, right? So if good of mid, if what does it mean by good? Good means that if this penalty is, and we'll define it more specifically. I just write it down then. Right. So that means that good, a target is good if the penalty, the target penalty, is successful, is possible, right? Put it that way, right? And for now, we'll put a pass. So okay, so if this is possible, then we want to try a bigger number, right? So we set left is equal to mid, else we try smaller number. Actually no, I got it the wrong way. Sorry. Because if it's good, then you want to try, for this problem, you want to try a smaller number, right? Otherwise, you want to try a bigger number because smaller numbers means that you used up more k, right? And then now we just return left. Because at this point, after this loop, left is equal to right? Or like within, again, 2 to the 100th power position. Well, 10 to the 8th over 2 to the 100th, but whatever. It's good enough, right? We just don't have enough bits to represent it technically. I guess in a float or double position type situation, I know there's the exponent, which technically could go to like 127 or 255. I don't even remember anymore. I don't know. These are things you can look up, so I don't know, right? Yeah. Okay. So then now this is like we said, we're just gonna be greedy. So here, how do we want to write it? Well, let's just say used is the number of k used, right? And then now we maybe we do last is equal to stations of the first one, right? Yeah, and then now maybe we do it for s in stations after the first one. We go, okay, well, if so then now we just try to figure out how many k's we need, right? Between, I guess that's a different way of writing it. I mean, we could do it this way and then just do it, but you can actually do like previous, current, right? In SIP, basically just look at adjacent stations, right? Because you can't move the current station, so then you're just figuring out how many you put in between, and then it's just about the delta, right? Delta is equal to current previous, and that's it. So then delta now is delta over target is the number we used, right? Because if the space is 10 and your target is 5, then you put 1 to make into 2 parts of 5 each. Okay, so I mean it's gonna be just minus 1 maybe, but or it's the ceiling of it maybe, right? So because for example, if you have, and this is the way I usually do it, is I use real numbers and try to figure it out because I'm really bad at math. So for example, if the space is 10 and we want to make the maximum penalty 3, then now we put 1 on 3, we put 1 on 6, and we put it on 9. So it's going to be the ceiling of this minus 1, right? I think that's right. And then we add it to used, and then we just check if used is less than or equal to k. That means that this is good. All right, that's it. Let's give it a spin. Let's give it a submit. Okay, cool. I mean, I think the reason why I hesitated a little bit is because when you use things like ceiling, it is very prone to position errors. We probably could have written this a little bit better. Actually, I mean, it's tough because target is actually a float, right? I don't know if I could have written this a little bit cleaner. Because you can imagine that if the ceiling of like 5.99999 is going to be 6, but 6.0001 is 7, right? Which is a little bit awkward sometimes, but okay. Well, for this input, it is fine. So we're going to be happy to go to sleep. Yeah. And if this is too much precision to you, you can actually just make it a little bit faster, right? And yeah, boop. And then now we jump from like the end to the beginning, and you can play around the position. It doesn't really matter. But yeah, so what's the complexity here, right? Well, this is going to be linear time, as you see. Hopefully, no magic trick. You can figure out the explanation. This is technically over B, where B is the number of bits. You can probably be more precise about it versus a 50 bound, but again, 2 to 50 is also going to get you, within that number, so I don't worry about it. But yeah, that's it. That's all I have for this one. Let me know what you think. Thanks for watching. Oh yeah, I didn't actually go. I mean, this is over B, where B is the number of bits, times N, where N is, well, the input size, right? And that's it. Yeah. We're going to go pass out. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.